Okay, so in section 5.9, these are two sections that are in the honors course. So I know we're not going in order, but I thought during Thanksgiving week, it's kind of nice to fit them in. So we're not doing any other topics. So we are going to talk about arithmetic and geometric series. We're going to do it algebraic, graphically, and numerically. So first, let's talk about the difference between, we'll see the word sequence and we'll see the word series. So both of these refer to a pattern. A sequence specifically is like 2, 4, 6, 8, 10, dot, dot, dot. Okay, so a sequence is a list of numbers that are in a pattern. A series, so we'll just put this in purple. A series is specifically if I would take those it's a sequence, same numbers, and I would add the terms. Okay, so that's really the difference. I might even mess up and use the words interchangeably. You might, because they kind of mean the same idea. And when we want to add them together, we usually use other words to refer to them, but that's the difference. Okay, so two types of sequences. So a sequence is just going to be a list. So a sequence in general is just a list of numbers that follow a pattern. And there's tons of patterns, okay? So we're only going to talk about two of these patterns specifically because then we can do some more things with them. So the first one is the definition. So arithmetic, by definition, is a sequence whose terms are generated by adding the same number. Now, I said adding, but I can also add a negative. So you can think of it as subtraction, okay? Geometric is a sequence whose terms are generated by multiplying the same number. Now, I can multiply by a fraction, so it might look like you're dividing, okay? But by definition, arithmetic is adding the same number and geometric is multiplying, okay? So let's do some examples. So on arithmetic, I can do 5, 10, 15, 20, and then dot, dot, dot. We typically, for the number that you're adding or subtracting, we call that the common difference. And we let it be abbreviated with the lowercase d. Okay, and so on this pattern, well, you figure out what am I adding each time? Well, 5. So our common difference would be 5. Now I could have another pattern. Let's say I did 100, 97, 94, 91. And so I think, oh, well, I'm really subtracting 3, but that's the same as adding a negative 3. So your pattern might look like subtraction, but I can really add a negative. So on this sequence, my difference would be negative 3. Okay? All right, let's do geometric. So on geometric, let's say I did 5, 10, 50, 250, dot, dot, dot. The number that we're multiplying is actually called the common ratio, and we let it be an r, a lowercase r. So we figure out, well, what are we really multiplying by here? And if you're not sure, oops, hold on, I've already made an error. That's what I get for doing it in my head. Okay, so 125, okay, so on this one, I can figure out what am I multiplying by. And if you're not sure, you can always take a second number and divide it by the previous number. Sometimes you'll be able to tell, okay? So if I tell you something is geometric and I want the ratio, you can pick any two numbers to compare and figure out what you're multiplying by. Same idea, what if I had 100, 50, 25, 12.5, 6.25, ... Well, our number is getting smaller, so I can think, what am I multiplying by? Well, same idea. I can take any second number and divide it by the previous number and reduce. These both divide by 50, so we get 1 over 2. And so you can think like, oh, if I went backwards, I'm multiplying by 2, so I really needed to multiply by a fraction, 1 over 2, okay? So you don't say what you divide by, you always say what you're multiplying by. That's by definition. All right, a general formula is an equation that can be used to find any term quickly. So there are some advantages for you writing an equation, or if you're given an equation, for you to find different terms. So for arithmetic, our general formula is a sub n equals a sub 1 plus n minus 1 d. And I know this looks like a lot, and it is, but let's talk about what they mean. So a sub n means any term, and we'll do an example. A sub 1 stands for the first term in the sequence, okay? N is the number of terms, and typically you leave this, leave as n if it's a formula. And then D is your common difference. What did you add or subtract by? Okay. So let's go ahead and do an example while we're here. So let's say, write the general formula for this sequence, and they give us that, okay? And so I notice, well, what's the pattern? Well, I'm subtracting 6, subtracting 6, subtracting 6. So I know that this is arithmetic. So first you want to identify that it is an arithmetic sequence. Then when you know it is, we're going to write the formula. So in a general formula, you want to keep a sub n. Okay. Our first term is 50, so we're going to substitute. N minus 1, you want to leave that as n, so we're going to leave that alone. And then I need to find the common difference. So we subtracted 6 each time, so that's our common difference. Now, from here, I need to actually clean that up. So the way we clean this up is we're going to distribute that negative 6. So 50, and then negative 6 times n, and negative 6 times negative 1. And then we can combine those like terms. So our general formula is negative 6n, and then 50 plus 6 is 56. Okay? And so what happens is I might say find, I'll write it over here. This would be a different problem. I would say find the 100th term. Okay? Well, you have choices. I could write out 100 terms, but that just takes so long. The nice thing is once you have this formula, then what I know is that n equals 100, and so I can substitute 100 into that formula for n. And then we can find it really quick. So negative 600 plus 56 is negative 544. Without finding any other terms, I was able to find the 100th term pretty quick once I knew that formula. So that's kind of the advantage of learning how to write a formula. Okay. All right, geometric formula is going to be a little harder to clean up, and you won't usually want like the 100th term, but so this is a sub n equals a sub 1 times r to the n minus 1 in the exponent. A sub n still means any term, and you typically want to keep this. A sub 1 is the first term. R is that common ratio. What did we multiply by? And then n is the number of the term. And you typically want to keep this too in your formula. Okay? All right, so our example says write the general formula for that pattern. So we got A sub n. What we notice is we're dividing by 2. So remember, if you divide by 2, that means your ratio is 1 divided by 2. So we know that this is geometric because that was our pattern. And then we can fill out what we know. Our first term is 100. Our ratio, typically you put this in a parenthesis so you know it's not 100 times a half. And then n minus 1, that's your exponent. Now, this formula you can't really clean up. So we're just going to leave that alone. Now, this one, let's say, okay, that's done. Let's say on this one, I wanted to find the 100th term. Well, that means that n equals 100. So I would have 100 times 1/2 to the 100 minus 1. And there's not much we can do, but I can write it as 100 to the 1/2 to the 99th power. This is so tiny, your calculator's probably not going to even be able to find it. It'll just say 0 with a bunch of decimal places after it. So this would be A sub 100 because n is 100. And so that means the 100th term when you write A sub 100. Okay, so typically finding the term, we prefer doing it on the arithmetic just because you can clean it up and things like that. All right, so let's look at a graph. Now, if we kind of use what we know, let's just use this. Okay, so that means my first term is 50. My second term is 44. My third term is 38. Okay, and I know this is hard to see, but we're going to say like this is 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay, and so this is 1. So on my first term, we've got 50. Our second term is up 44. So that was 40, 1, 2. This is 2. 1, 2, 3, 4. So they're 2.5. So 2 and then 40. Mine's really tiny, and I know yours is too. Okay, so 44, we're going to be a little bit less. I'm trying to make this. I know this is really tiny. 3 at 38, so here's 3, and then we're going to go up. Uh, 4 was 32, so 4, 32. Okay, and if I would keep going, what's going to happen is it's going to follow a pattern. Okay, and so really it's linear. That should make sense because it's into the first. So it really is a linear equation. On our geometric, let's do the same idea, except we're going to make these tens. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So our first term is 100. Our second term is 50. Our third term is 25. Our fourth term is 12.5. Our fifth term is 6.25. And then we would keep going. This one, and I know you haven't learned this yet, you're going to learn this and talk about this more in Sec 3, but this is called an exponential curve. And what happens is as we keep writing our terms, they actually get smaller and smaller and smaller, closer to zero, but they stay positive. Okay? So you can tell just by given a graph if it's arithmetic or if it's geometric. That's kind of the idea. Okay? Now, our sum formula, you have two choices. You could either add all the terms by hand or by calculator, let's say, because you could use a calculator, or you can use the sum formula. Obviously, the sum formula is really nice if you're given a lot of equations, a lot of terms. So on arithmetic, our sum formula is n over 2 a1 plus an. Now, let's see what this stands for. N is the number of terms that are in the sequence, and it'll say like add the first 50, and we're going to use it on the modeling. A1 is the first term, and AN is the last term in the series. So it depends on how many they want you to add, okay? The geometric SN, it's S for sum, is A sub 1 minus R to the N, parenthesis, 1 minus R. So you do need the parentheses when you type that into a calculator. A1 is the first term. R is the same, just so you know. That's the ratio, what you're multiplying by. And N is the number of terms that they want you to add. Okay? We are going to use these. You can use them for just a list, or you can use them in an application. I just decided to show you how to use them in an application. Okay. All right, so let's look at our modeling. So, Mrs. Eden, I do drink Diet Pepsi. I've actually stopped, but I still have one every now and then. So I decided to build a pyramid-shaped sculpture. Think of it like this, where for my daughter to knock down. The top row has 8 cans, so we'll put 8 here. The second row has 10 cans, 12 cans. So we'll say row 1. I like to get pictures. And so on. How many do I need for the 15th row? Okay, so I want a specific term. Now, you always have the choice, because 15 isn't that long. You can find the pattern and you can write out 15 on your own. Okay? But I don't need to show you how to do that. If you want to do it, you're welcome to. I always like to think, what if I would have asked for the 115th term? You know what I mean? So let's see how we would do that. So that means we want to use the formula. So A sub n equals A1 plus n minus 1d. So if we want the 15th term, that means that n equals 15. My first term is 8. The number of terms that I want are 15. And what is my difference? Well, I see that I'm adding 2 each time. So then I can just type all of that straight into a calculator. So our 15th term is 14 times 2 is 28. 28 plus 8 is 36. And that's it. I didn't have to find anything else. I think that's quicker sometimes than writing it out, but especially if I wanted to find a big term, okay? All right, let's go ahead and do this sum formula because it's very similar. So the only difference now is I say, hey, how many total will I need? So that means that I actually have to add all these up. So once again, you can list them all separately, or you can use this sum formula. So I'm going to go back up here and I'm going to write that down. Okay, because I said, what if I needed the 100th row? Well, nobody wants to write out 100 numbers. So our sum, so we want the sum of 15 rows. So n over 2, a1 plus an. So the sum of the first 15 numbers, because n is 15, so I've got 15 over 2, and then I need to find the first term, which remember was 8, and then my last term is my 15th row, and we just found that. So if you didn't find that, you would have to, okay? So then I can type that all straight into a calculator, and it adds it up for you, which I just think that's crazy. So we would need 330 cans all together. Okay, so that's how we could use the sum formula. It definitely is more helpful the bigger the amount of terms that you need to use. All right, geometric is very different. So this is kind of the famous geometric sequence problem. It says on day 1, you can try this with your parents. You are going to start with a penny, like literally 1 penny. That's it. And then every day you double the amount. So on day 1, you have a penny. On day 2, we're going to double that. So that means I get 2 pennies. And then on day 3, I get 4 pennies. On day 4, I get 8 pennies, okay? And so ask your parents to do this just for 1 month. Like literally, it's funny. So what I want to know is by the end of the month, and we're just going to use 30 days, how much money will you get on that 30th day, okay? And so it's a specific term. Well, I can list out 30 numbers, but even I don't want to do that. So we're going to go back up here, and we're going to use that arithmetic formula. So a sub n equals a sub 1 times r to the n minus 1. So on our 30th day, so n is 30, my first term was literally a penny. My ratio, well, if I double it, that means that my ratio is 2 because I'm doubling it. And n is 30, so 30 minus 1. You're going to want to use a parenthesis. So we're going to type that into a calculator. Just make sure you use parentheses when you need. And you should end up with 5368709.12. And I'm not even kidding you. On the 30th day, just by starting with a penny and doubling that amount, you will get $5 million. It doubles that quickly, and it doesn't seem like it. You'd be like, oh, I bet you're going to get like $300. No, it's really $1 million. 5 million. Okay? So let's try a modeling sums. Now this one's a little different. A job contract states that we will start earning $12,000 a year and we will see a 5% raise every year. How much total money will I get in 10 years? So it's going to take each yearly income with my raise and tell me all together how much money I would make. So that's the idea that it's a sum. Because it's a percentage, that is your clue that we're multiplying and it's geometric, okay? So my formula is a sub 1 minus r to the n, all over 1 minus r. Now, the way my ratio works, we need a little bit of background information because I know this is new for you, is you want to take 1 plus your rate as a decimal. Okay, so since I start out at 5%, the way you change it to a decimal is you divide it by 100, or you move your decimal 2 places to the left. So it's actually 1 plus 0.05, which is 1.05. That's my ratio. The 1 makes sure that I'm going to include that 12,000 plus my 5% raise. That's why we put the 1 there. So our sum of 10 years, well, my first term was 12,000. And then it's 1 minus 1.05 to the n, we said 10. And then parenthesis 1 minus, my ratio is 1.05. And you want to type that straight in with the parentheses and everything. Since this is money, we always go to 2 decimal places. And this would be a problem that would be a lot harder to do by hand because of that percentage. So being able to do it all together in a calculator is actually really nice. Okay, so I get the sum after 10 years by adding all of it together is 150,934.71 because it's money. So I would actually make in 10 years $150,000, which is pretty decent. Okay, so use these notes and I want you to try the practice problems that are on the assignment. It says it's a quiz, but you can retake this and do your work on separate paper and just answer the questions. Okay, so email me if you have any questions.